All right, students, let's work through the free response questions. And looks like here, this first one's looking like a conservation of energy one. But again, we've got to some harder materials. We got to our rotations and our center of mass. So this can be a bit of a challenge one. So I hope you did well and probably got, some lots of partial credit, if not the whole thing right, but at least maybe close to it. Because watch this and notice the marks here for the center of mass. And that's going to become crucial here because, potential energy has to do with how high the center of mass is. And we want to keep that in mind. So we have a solid ball with a diameter of 5 centimeters. It starts with its center 33. And so they do a good job here of helping us out and saying this is 33. I'm going to put it in meters though, 0.33 meters above the ground on a ramp that has a loop that has a diameter. And so the whole diameter here is 20 centimeters, which I'm going to put as 0.2. But notice then that the center of mass of the ball here is down by 2.5 centimeters because the diameter is 5 centimeters. Or maybe stated another way, note then that this is only 17.5, which I'll write in meters, centimeters above the ground. Because as they say here, the ball rolls without slipping down the ramp and around the loop. What is the translational? And don't forget then, since we have things rolling now, there is a translational speed and a rotational speed. And so we got to be clear which one they're looking for and which one we're thinking about. What is the translational of the speed when it is at the top of the loop here? So using conservation of energy, so I'll say initial energy is equal to final energy, I can start by saying, well, it only has gravitational potential energy. So I'll say mgh initial, that's its initial potential energy. But as it comes down, goes around the loop here, on the other side, it has a translational kinetic energy as well as a rotational kinetic energy, as well as being off the ground a little bit. So it has some gravitational potential energy. And that, hopefully, is what you did, that you included both kinetic and rotation, and you also included the potential that it has, including the fact that the center of mass isn't quite 20 centimeters up. It's only 17 and a half. And so as I fill this out, I notice that they don't give me the mass of the ball. So I'll just leave that as a little m, put 9.8, and the height as 0.33. Again, they don't give me the mass here, and the velocity is what I'm looking for. So there's not much I can do there. Then this is where it gets to the hard stuff, the rotation. I need the moment of inertia of a solid ball, a solid sphere. And so looking in my table here, I'm trying to remember what chapter that was. Was that one? See, I got the book here. Where does the book do rotation? Rotational motion, torque. It might be in chapter 10. But we also did torques. Yeah, dynamics and rotation. Rotational inertia. Yeah, 10.3. There it is. So in the table in section 10.3, you'll see a 2/5 mr squared, where m is the mass of the ball, which I don't know, and radius. Radius I do, but I'm going to hold off putting it in because angular speed is linear speed over radius. And so the r's are going to cancel. So you can either put them in or not because they're going to cancel off. The M, the 9.8. And again, this is that final height, which we need to be careful with. And say it's the height of the center of mass. And so I can easily see people putting a 0.2 here. Now notice then that there is an M in every term. And so now it makes sense why I didn't need to know. This would be a true for ball. Any solid ball that had any mass. So independent of the mass. And the radius cancels off, at least here. I don't need to know the radius, but I did need to know the radius for this step. So, excuse me, noting the radius was important. And so maybe I will do this term. Yeah, maybe I'll do this term. Because now I see that I have a 1/5 v squared and a 1/2 v squared. So that's a common denominator of 10. 5 plus, excuse me, 5 plus 2 is 7 v squared. And then this number, why don't I just do this? 9.8 times 0.33 and subtract off 9.8 times 0.175. And so this is 1.519. And so to finish this calculation, I'll go times 10 and divide by 7, excuse me, and then square root of all that. It should be the speed. And so 1.47 meters per second should be the translational speed. Let me just grab my glass of water here. Oh, that was good. Take a big gulp. That was cool. Something in my throat. All right. So there's the first of our free response questions. Let's go on to the second one. Looks like our fluids one. This was, I think, our chapter 11 stuff. I should have said that on the multiple choice. That was that number 10 was a fluid one too. And it looks like there's two parts. Part 1, a block of wood that has height of 9 centimeters, length and width of 20 centimeters, and a density of 0.333, that's about a third, is placed in water. As it floats on the surface, what depth is below? Okay, so this is our straightforward problem. I think 2 is going to get a little harder on us. But if it's just floating, and so it's kind of what this picture is, the buoyant force lifting up on the wood is equal to the weight of the wood. And the weight of the wood is just the mass of the wood times G, and mass of the wood is the density of the wood times its volume of the wood times G. Now, buoyant force, this is Archimedes' principle, is equal to the weight of the fluid displaced. So this would be the mass of the, and I'll put H2O that has been displaced, and I'll even come up here in my picture and kind of show you that the water that's been displaced is kind of in this section. And that's what I need to kind of figure out. But I'll go ahead and write the mass of the H2O, kind of like I wrote the mass of the wood, as the density of the H2O times the volume displaced times G. There is a G on each side, so I won't need to worry too much about that. So now I can take the density of water, which is 1 gram per cubic centimeter, and the volume displaced, well, since the block is sitting down, it would be H times the length and the width. So 20 times 20. Now the density of the wood is the 1/3. And the volume of the wood would be the capital H times 20 times 20. And I wanted to just write out the 20s because they would cancel on each side. And so what you get really here is, I'll just write it as 1/3 of H, which is 9, which is our 3 centimeters. So it's something that we did in class and talked about, that something floating on the water, the percentage under the water is the ratio of the densities, kind of makes sense. And so we have about a ratio of the densities is 3 to 1. And so the ratio of the two volumes displaced are 3 to 1. And so the heights are 3 to 1. So nothing too shocking or surprising there. But let's go to part 2, because that's going to be a little bit more here, where it says, now, what maximum volume of lead, and then they give us the density of lead, that can place on top of this wood so the whole wood-lead system does not sink. So you can see that you're, adding quite a bit of weight, and that's going to be forcing the wood down lower. And of course, the reason is back here. Anything that's floating means that the buoyant force has to equal the weight. So as you start to put more weight on there, you're going to need more buoyant force. And you get buoyant force from the volume displaced. And so this has got to sink deeper in the water. That's why when you load a boat, it goes deeper, 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 deeper. That's why, you can't overload a boat if you're in a shallow harbor or a bay or something. It's like, hey, wait, we're getting down close to the bottom. We're gonna rub the bottom, and so you need another. You got to be careful with the bottom, or change the weight. Anyways, so let me kind of draw a picture, and so kind of the first picture that's going to my mind is this. If this is kind of the water line, as I pile on lead, I can get that whole block of wood to go under water, my lead holding it down, if you will. And that's kind of the first picture in my mind, but it's not complete. Because now that I think about it, if I start to put even more lead on top, I could actually get even more buoyant force, because something where the lead is partially submerged. So if this is the wood, and then this is the lead, I could get something like that. And I think you see now where I'm going with this. The most you can do, and that is the largest buoyant force you can have, is when you displace the most amount of water. And once both the wood and the lead are under water, you can't displace anymore. And that is going to get your maximum buoyant force. So your buoyant force, I'll even put maximum, is then really the weight of the water displaced by both of these. And I'll just go weight of H2O displaced by both wood and lead. So that's the key thing to it. And of course, the weight of the system is, of course, the weight of the wood. Oh, I think my pen's drying out. Let me grab another one. And the weight of the lead. Okay, so keeping that in mind here, I'm just going to make the same argument I did in part 1, that this thing is just at its maximum load of lead here when it's completely submerged, both of them. And so let me find each of these and then set them equal to each other and then solve for, what are we after? The maximum volume of lead. So we're going to try to find this volume of lead. All right. We'll call this page 1. So on page 2 here, I'm going to start and just say, okay, so when does the buoyant force equal the weight of the two objects? So I'll put my equal sign here in the middle because there's two of them. Maybe I'll start with the weight then. There would be the mg. Let me just jump right from mg to rho vg for weight. So this would be the density of the wood times the volume of the wood times g. This would be the density of lead times the volume of lead times g. So there's the weight of the two. And like we did in part 1, over here, the buoyant force is the weight of the displaced water. So it would be the density of the water times the volume of displaced, which in this case would be both the wood and the lead, times G. And like we saw in part 1, the G doesn't really come into play here at all. And so now I can put in my numbers. The density of the water is 1. The volume of the wood would be 9 by 20 by 20. The volume of the lead is what I'm looking for. Okay, good. The density of the wood is the 1/3 times the 9 times 20 times 20 for the volume of the wood. The density of the lead is the 11.3, and then we got the volume of the lead. And maybe right here I'll take the volume of the lead. So this is 11 times the volume of lead. This is 1 times the volume. I move it to that side, and I would subtract 1. So 10.3 volume of lead from here. Now, over here, I've got a 9 times a 20 times a 20, which I guess is 3,600. And then over here, I guess I have the 3,600 and then a third of that. So that's a 1,200. And so my volume of lead is going to be the 36 plus the 12 added together, divided by 10.3. And it looks like 466. And I guess I haven't been real clear on my units, but this 9 and 20 and 20 are in centimeters, and so this is the 466 cubic centimeters. All right, nice. That was, yeah, a little involved one there. I like it. In fact, with enough involved that maybe I'll do a quick check here. If this is the volume, the weight then should be 1/3 times the volume of the wood, 3,600, plus 11.3 times 466. Okay. That should come out to be the same as this side of the equation, which is, it doesn't seem quite right. 1,200. Ooh, 48. What did I do wrong here? Weight of the wood. Is that right? 9 times 400. Yeah. Ah, that's it. My bad. Didn't I need to subtract these? Ah. Okay. That would be 36 minus there. All right, so 3,600 minus 1,200. Then divide that by 10.3. 233 cubic centimeters. Good, I feel a little better about that. That just seemed too big to me. But let me, okay, so now let me also check that one here. So the weight would be 0.33333 times the 3,600. And then the 11.3 times 233. 38. And 32. And then that should be the two volumes added together. And that's 36 times, that makes 38, 33. Yes, they match. Okay, good. So sorry about that little error there. Glad I